Black holes. They are the ultimate cosmic enigma, places where time and space break down, where gravity becomes unstoppable, and where light itself cannot escape. They are some of the most mysterious and terrifying objects in the universe. But what if black holes aren't just cosmic death traps? What if there's something more, something bigger? Here's a thought. What if our entire universe, vast and full of galaxies, is actually the inside of a colossal black hole? To understand this extraordinary idea, we need to start with the basics. What is a black hole? Simply put, it's a region of space-time where gravity is so intense that nothing, not even light, can escape. Black holes are born when massive stars collapse under their own weight, compressing matter into an incredibly dense point called a singularity. This singularity is surrounded by an invisible boundary known as the event horizon. Anything crossing this line, matter, light, even time itself, is lost forever. These strange objects are not just science fiction. They were predicted by Einstein's groundbreaking theory of general relativity, which showed that massive objects warp the fabric of space-time itself. And black holes? They're space-time taken to the extreme. But black holes might be even stranger than we thought. Some scientists propose that they're not just points of destruction, but cosmic gateways, places that might even hold entire universes within. This idea might sound impossible, but as we delve deeper into the mysteries of black holes, you'll see why scientists are asking, could our universe itself be inside one? What are black holes? Black holes are some of the most mysterious and fascinating objects in the universe. They're places where gravity is so intense that not even light can escape. But what exactly are they, and how do they form? Types of black holes. There are two main types of black holes. First, we have stellar black holes. These are the remnants of massive stars that have reached the end of their lives. When such a star runs out of fuel, it collapses under its own gravity, compressing all its matter into an unimaginably dense point called a singularity. Stellar black holes are surprisingly small, typically around 16 kilometers or 10 miles wide. To put that into perspective, they could fit comfortably within a small city. Yet, these tiny objects have masses that are several times greater than our Sun. Then there are supermassive black holes. These giants sit at the centers of most galaxies, including our own. Sagittarius, A*, the supermassive black hole at the center of the Milky Way, has a mass millions of times greater than the Sun. Despite their immense size, these black holes remain invisible, cloaked in darkness. What we see is their accretion disk, the glowing matter spiraling toward them. Supermassive black holes can be millions or even billions of kilometers wide, dwarfing anything else in their vicinity. But how do black holes form? It all starts with a star. Stars are held together by the delicate balance between gravity pulling inward and the pressure from nuclear fusion pushing outward. When a massive star runs out of fuel, that balance collapses. Gravity takes over, and the star implodes. This implosion compresses the star's core into a singularity, a point where matter is infinitely dense and space-time itself is distorted beyond comprehension. Around this singularity is the event horizon, the boundary of the black hole. Think of it as the ultimate point of no return. Anything crossing the event horizon, light, matter, even time itself, is lost forever. Scientists believe that millions of black holes exist in the Milky Way alone. Most of these are stellar black holes, remnants of ancient stars that have lived and died over billions of years. Yet many remain hidden, invisible against the dark backdrop of space. So how do we find something that doesn't emit light? Astronomers look for the effects black holes have on their surroundings. For example, When a black hole pulls in nearby gas and dust, the material forms an accretion disk, glowing as it heats up while spiraling toward the event horizon. These bright emissions help us identify the presence of a black hole. We also detect black holes by observing their gravitational pull on nearby stars and objects. For example, Sagittarius A was discovered by tracking the motion of stars near the center of our galaxy. Their rapid orbits revealed the presence of an invisible, supermassive force. Black holes are more than just scientific curiosities. They are reminders of the universe's incredible power and mystery. From the remnants of ancient stars to the massive giants shaping galaxies, black holes challenge our understanding of time, space, and gravity. What happens near a black hole? Black holes are not just fascinating objects. They're regions of unimaginable power. Near a black hole, the rules of physics twist and stretch. The closer you get, the more extreme and terrifying the effects become. Gravity near a black hole is so intense that it can shred matter apart. This process begins well before anything crosses the event horizon. Let's start with a phenomenon scientists call spaghettification. Imagine an object or even a person falling toward a black hole. The gravitational pull on the side closer to the black hole is much stronger than the pull on the far side. This difference stretches the object out like a piece of spaghetti. Eventually, the object is torn apart into individual atoms. This isn't just theory, it's the brutal reality of what happens near a black hole. But not everything falls straight into a black hole. Matter often forms an accretion disk, spiraling around the black hole at nearly the speed of light. This spiraling motion creates immense friction, heating the matter to millions of degrees and causing it to emit powerful radiation. Accretion disks are among the brightest objects in the universe, often outshining entire galaxies. But they're also deadly. The radiation and heat they produce are so intense that anything nearby would be vaporized. Sometimes, black holes produce something even more spectacular: relativistic jets. These are powerful streams of particles ejected from the poles of a black hole at nearly the speed of light. These jets are created by magnetic fields surrounding the black hole. As matter spirals into the accretion disk, the black hole's intense rotation twists the magnetic fields, launching particles far beyond the galaxy it resides in. These jets can stretch for thousands of light years. One of the most famous examples is the supermassive black hole in the M87 galaxy. Its jet is so massive, it extends over 5,000 light-years into space. To put that in perspective, that's 50 times the width of the Milky Way's central bulge. But what would happen if Earth encountered a black hole? Let's imagine a scenario where our planet is pulled toward one. As Earth gets closer, the gravitational pull from the black hole would create immense tidal forces. These forces would stretch and distort the planet, triggering catastrophic events. Volcanoes would erupt violently, releasing rivers of lava. The oceans would churn into massive tsunamis, and earthquakes would tear the continents apart. Even before Earth crossed the event horizon, it would be unrecognizable, a fiery, broken world consumed by chaos. And once it reached the event horizon, spaghettification would tear the planet into atoms, leaving nothing behind. This grim scenario reminds us of the raw power black holes possess. They are not just cosmic anomalies, they are forces of destruction on an unimaginable scale. But as terrifying as black holes are, they also inspire awe. The forces they unleash shape galaxies, create new stars, and scatter elements across the universe. They remind us of the delicate balance between destruction and creation. In the end, black holes are not just destroyers, they are sculptors of the cosmos. They teach us that even in the face of immense power, there is beauty, mystery, and the potential for discovery. Near a black hole, the laws of physics are pushed to their limits, and yet these regions of chaos and wonder continue to captivate our imagination. What other secrets might they hold? The universe as a black hole interior. What if the universe itself is the inside of a colossal black hole? It's a question that pushes the boundaries of science and imagination, but it's one that some physicists believe could hold the key to understanding existence itself. Black holes are born when massive stars collapse, compressing all their matter into a singularity, a point of infinite density. This singularity is so extreme, it warps space-time beyond recognition. But here's where things get even stranger. Some scientists propose that the singularity at the heart of a black hole might not just destroy matter. It could give rise to an entirely new universe. The gravitational forces compress matter to such an extent that, through a process called quantum tunneling, the black hole creates a Big Bang, birthing a new cosmos on the other side. This theory suggests a cosmic cycle. Black holes collapse, new universes emerge, and the process repeats. It's a tantalizing idea that connects the mysteries of black holes to the origin of our own universe, the Big Bang itself. But there's another mind-bending theory tied to black holes, the holographic principle. Imagine that everything in our universe, all the stars, galaxies, and even you, is actually a projection of information stored on a two-dimensional surface. In this view, the event horizon of a black hole acts like a cosmic library, storing information about everything that falls into it. The idea is that all the complexity of our 3D universe could be encoded on a 2D surface, like a hologram projected into space. This theory challenges our understanding of reality itself. Could everything we experience be a 3D illusion created by the information on a black hole's boundary? Some scientists take the idea even further, suggesting that black holes could act as bridges between universes. These bridges, called wormholes, could allow matter and light to travel from one universe to another. Imagine a black hole in our universe leading to a white hole in another universe. A white hole is the opposite of a black hole. It ejects matter and light instead of pulling it in. While purely theoretical, white holes hint at the possibility of cosmic recycling, where what's consumed in one universe is reborn in another. Could these wormholes be gateways to parallel universes? Could the matter we lose in black holes reappear somewhere else, creating entirely new realms of existence? One of the most intriguing ideas comes from a theory called loop quantum gravity. This theory suggests that black holes don't collapse into infinite singularities. Instead, quantum effects create a sort of bounce, preventing the complete collapse of matter. In this view, a black hole's collapse could lead to a Big Bang, where the matter and energy compressed within are released into a new cosmic space. Our universe, according to this theory, might be the result of a black hole that existed in a parent universe billions of years ago. This idea not only explains how black holes might create new universes, but also ties together the quantum and cosmic scales, uniting the very large with the very small. These theories push the boundaries of what we know and what we can imagine. If our universe is the interior of a black hole, it raises profound questions about our place in the cosmos. Are we part of an infinite cycle of creation and destruction, where universes are born and reborn? Is reality itself a holographic projection, encoded on the edge of a cosmic abyss? One thing is certain: black holes are not just ends, they are beginnings. They are not just destroyers, they are creators. And within their dark depths, the secrets of the cosmos might just be waiting to be discovered. Challenges and counterarguments. The idea that our universe might exist within a black hole is fascinating, but like all scientific theories, it faces significant challenges. To truly understand the possibilities, we must also confront the unanswered questions, physical limits, and competing ideas. One of the biggest challenges to this theory is the lack of direct evidence. While we've observed the effects of black holes on their surroundings, we've never seen what happens beyond the event horizon. Everything we know about black holes is based on indirect observations and theoretical models. Additionally, the idea that black holes could birth universes remains speculative. While some features of the Big Bang, like extreme density and energy, mirror the conditions inside a black hole, the connection is far from proven. There are alternative explanations for the origin of the universe that don't rely on black holes. For example, the standard Big Bang theory describes the universe's birth as a singular event with no need for a black hole parent. The evidence supporting this includes the cosmic microwave background radiation and the expansion of space itself. Black hole-based theories, while intriguing, don't yet have the same level of observational support. Another major challenge lies in the extreme conditions near black holes. The concept of infinite density at a singularity pushes the limits of Einstein's theory of general relativity. At these scales, the equations break down, leaving us with no clear understanding of what actually happens. General relativity describes how gravity works on large scales, but it fails to explain the quantum effects that dominate at the smallest scales near a singularity. Without a unified theory of quantum gravity, our understanding of black holes remains incomplete. White holes, the hypothetical counterparts to black holes, also pose significant problems. In theory, a white hole would eject all the matter a black hole absorbs, but this idea is unstable. No white hole has ever been observed, and many physicists argue that they cannot exist in a universe governed by the second law of thermodynamics. Finally, we must consider competing theories that challenge the idea of black hole universes. One of the most prominent is the multiverse theory. This theory suggests that our universe is just one of many. In this view, new universes aren't created by black holes but by quantum fluctuations in a larger multiverse. Each universe might have its own unique laws of physics, existing independently from the rest. While the multiverse theory is equally speculative, it provides an alternative explanation for why our universe has the specific conditions needed for life. If there are infinite universes, it's not surprising that at least one, ours, has the right conditions. The multiverse theory and black hole universes are not necessarily mutually exclusive. Some scientists speculate that black holes could create new universes within a multiverse, bridging the two ideas. But without evidence, these remain intriguing possibilities rather than confirmed truths. The challenges to these theories remind us of the limits of our understanding. Black holes and the origins of the universe push the boundaries of what we can observe and measure. They force us to grapple with the unknown, to confront the mysteries that remain just out of reach. Are black holes the seeds of new universes? Are we part of an endless multiverse? Or is the true nature of reality something even stranger, something we can't yet imagine? Science thrives on questions, and the greatest questions, the ones about our place in the cosmos, may never have simple answers. But it's in seeking those answers that we find wonder, discovery, and the drive to explore further. Black holes are some of the most mysterious objects in the universe. They challenge everything we think we know about space, time, and gravity. They're places where the rules of physics collapse, where the very fabric of reality is rewritten. But black holes may be more than just cosmic anomalies. They might be creators, birthing new universes in their depths. Our own universe, vast and filled with galaxies, could exist inside a black hole. This idea forces us to reconsider the boundaries of reality itself. Throughout this journey, we've explored the incredible power of black holes. We've seen how their immense gravity can tear objects apart and create spectacular jets of energy. We've learned about the strange possibilities of wormholes and white holes, and how collapsing black holes might lead to new universes. If black holes are gateways to new universes, then perhaps our own universe was born from one. The conditions inside a black hole, a point of infinite density and unimaginable energy, mirror what scientists believe existed at the very beginning of the Big Bang. Just as the Big Bang marked the birth of our universe, black holes could be the seeds of others. This connection between black holes and the creation of universes ties together two of the most profound mysteries in science. If our universe exists within a black hole, what does that say about the boundaries of reality? Is there an edge to existence? Or do black holes lead to an endless chain of universes, each giving rise to the next in an infinite cycle? This idea forces us to ask questions that go beyond science. If there are other universes, do they follow the same rules as ours? Could they be home to life, to entirely new forms of existence? Or are they realms so alien that we cannot even begin to imagine them? Perhaps every black hole in our universe is a doorway, a passage to another cosmos. And perhaps, just as we wonder about what lies beyond, there may be others in those universes wondering the same about us. As we look at the universe, we see not just stars and galaxies, but a tapestry of mysteries waiting to be unraveled. Black holes remind us that the deeper we look, the more questions arise.
Are black holes the end of everything, or the beginning of something new? Do they hold the secrets of creation itself? These are questions we may not answer in our lifetime, but they remind us of the endless possibilities that lie beyond the boundaries of what we know.